Okay, logarithms, or the logarithmic function, I suppose is another way of putting it. So logarithms and exponentials are the inverse of each other, so they're the opposite operations, which is why we tend to look at the two together. So say we'll look at logarithms now, and then when we come back we'll look at exponentials. So the actual definition for logarithms, because I suppose we're more familiar with index laws. So if y is a to the power of x, then x is the log of y base a. Now both of those things have base a. It's just that normally we don't say y equals base a to the power of x, we just say a to the power of x. But a is, of course, the base. So when we're looking at a log, we're basically saying a to what power will give us this answer y. And that's how we read a log. Now, we're going to see a more common one where actually e is the base, which is what we call the natural logarithm. And e is around about 2.717, something like that. And so then x would equal log y base e. But there is another way of writing that log, and that's simply ln, for logarithm naturel. It's French, you know. But if you look on your calculator, it's what you might have thought was the in button. But it's not actually the in button, it's the ln, or natural logarithm. The other way, if we see log without a base actually written, then we will assume we're talking about a natural logarithm. So if you just see log y, we're assuming. Now that's changed. If we go back 40 years, it used to be you would assume that was base 10. And that was before calculators, because your log tables, the common logarithms, were base 10. And that's what a lot of people worked with. So we used to just assume log meant base 10. But now with the advent of calculators, natural logarithms are used a lot more than the common logarithms. So base e is known as the natural logarithm. The graph of the log graph is similar to the exponential graph, but it's been rotated, I guess, if you like, and flipped a bit. So this would be the one where the base a is greater than 1. So just like with our exponential graph, you remember, has a y-intercept of 1. With a logarithm, it'll have an x-intercept of 1. So the log of 1 is always equal to 0. Doesn't matter what the base is. If a was in between 0 and 1, then it would be the blue curve here, so the upside down of that one. So if it was base a half or base a third and so on. And you don't have negative bases, same as when we're dealing with indices. We don't have negative bases when we're drawing the graph because, well, you can't get a nice continuous graph with negative numbers. Okay. So the sorts of things we like to talk about, domain, and we can see from our graph, domain is x is greater than 0. You can't find the log of a negative number. And the range is all real y. It is possible to get every answer using logarithms. So there are some log laws. You'll notice with the log laws, very similar to the index laws, but sort of like in reverse. Because when we were doing index laws, we said, oh, well, when we multiply, we add the powers. So this is sort of like the reverse. With logs, we add the logs. And that'll be the log of m times n. And the log of m minus the log of m will be the log of m divided by n. Now this is also now similar to something else that we've seen. Yeah, it's very similar to arguments. The log of m to the power of n will be n lots of log m. Again, that's similar to arguments. If we were finding the argument of z to the power of n, we'd have n lots of argument of z. Log of 1 is always equal to 0. That comes from the idea that anything to the power of 0 is 1. And if you had log a base a, then the answer must be 1. Remember we're saying, what number do we raise it to get this number? So a to the power of 1 would give you a. This one here is just highlighting that exponentials and logs cancel. So if you have base a to the power of log base a, the log and the base will cancel, leaving you with just x. So if the base is the same as the base in the logarithm, they will just cancel out. So if you had e to the power of natural log x, again, that would just be x. This is what's called the change of base formula. It comes in handy with a calculator, I guess, because some calculators, in fact most calculators, will only find the log of base 10 or natural log. So if you had to find it to a different base, your calculator is no good. But you can always change the base. And basically you choose whichever base you want to change it to. So you do the log of x of that base, but you divide it by the log of the old base. So if I had log, I don't know, say I wanted to find log of 10 base 5. So 5 to the power of what's 10, not an easy one to do. I could change that to base 10. I could say, well, that's the same as log of 10 base 10 of log of 5 base 10. And then I can do that on a calculator. I can get an answer for that. So we want to find log of 125 base 5. Again, you could look at it and just say, well, 5 to the power of what's 125? You've got the answer straight away. Or we could use the simple idea of equations of doing the opposite. If I want to undo the log, I'll exponentialize both sides, if there is such a word. So it now becomes 5 to the power of x is 125. The base stays the same. 5 was the base on the logarithm, so now 5's there. And again, you get that idea. 5 to the power of what gives me 125. So if you don't see it straight away, you can get it this way as well. And of course, 5 to the power of 3 is 125. This time we want to find the base. So x cubed is 343, that's basically saying. So again, if I exponentialize both sides, x cubed would be 343. Cube root of 343, 7. Well, the only difference here is I haven't said x equals. It's still the same question. Saying, oh, well, what is log 16 base 4? So 4 to the power of what, 16? Well, I can say, if I really wanted to show it, say they'd said show the answer was 2, then the middle step I could put in is I could say, well, all right, 16 I could rewrite as 4 squared. We then have that rule that says, the power I can bring to the front of the log. Log 4 base 4, well, that's got to be 1. And so then the answer is 2. That's if it was a show that question, you want to put all the steps in. But of course, in this one, it just said evaluate. So you could simply go, well, 4 to the power of what, 16? 4 squared, 16. Answer's 2. 6 to the power of 2 log 3 base 6. Now, the bases are the same, but I can't cancel them yet. I can only cancel it when it's to the power of log, not to the power of 2 log. So I've got to use my log law, which allows me to bring the power in this time. So 2 log 3 base 6 is the same as saying log 3 squared base 6. But now it's 6 to the power of log base 6. They will cancel, leave me with 3 squared, which is 9. Right? So you can't have a coefficient with the log when you cancel. You've got to bring that coefficient into the log, then you can cancel. Log 16 base 2 plus log 8. We could work this out straight away because 2 to the power of is 16, 2 to the power of 4, and 2 to the power of is 8. So we know this is going to be 4 plus 3 is 7. But all right, say we didn't see that. We could use our log laws and say, 16 times 8 is 128. 2 to the power of what is 128? 2 to the power of 7 is 128. So the answer would be 7. Plus means multiplied, minus means divide. So in this case, I'm going 125 times 32 divided by 4. Have to do it this way because I can't go 10 to the power of what's 125. That doesn't work out nicely. Same with the other ones. But when I do this calculation, that does work out nicely. Turns out just to be 1,000. So 10 to the power of 3 is 1,000. Looks tricky, but it's actually the change of base rule in reverse. Now, the top and bottom are to the same base, so I could simply rewrite that as log 8 base 2. Log 8 base 2. And then we say 2 to the power of what's 8, and that's 3. Log of 1/8, or rather the square root of 1/8. Well, the square root is the power of a half, so I can bring the half to the front. Now, 1/8. 1/8 is 2 to the power of negative 3. And so I get half times negative 3 on 2. Exponential equations. If I can rewrite them as the same base, exponential equations are very easy. So 1 on 27 I can rewrite as 3 to the power of negative 3. So they're both 3 to the power of something, so I simply solve 2x plus 1 is equal to negative 3, and we've got the answer. That's if we can write them to the same base. But you get more often ones like this. 2 to the power of x is equal to 9. I can't rewrite 2 to the power of 9. So we log both sides and take advantage of our log laws. The x now I can bring to the front of log 2. And so x equals log 9 divided by log 2. What you've actually done is basically use the change of base rule, if you think about it. Because you're now saying it's log 9 divided by log 2. So it's the same as log 9 base 2, which was the original question. 3.17 to 2 decimal places, that one. Okay. So 12a, let's play with our log laws. That's interesting. I've just picked one question out of 6b. I wonder what that is.